we already have at the department the lectures that are whose idea is to extremely established, very well established mathematicians of any ages, and then we have the other lecture that is meant for very young and promising mathematicians under the age of 40. The spirit of the Samuel Gitler's conference is a bit different, because it matches better also the spirit of Samuel himself, that was gregarian and generous with his mathematics. And so rather than concentrating only on one speaker for a week like in the other events, the idea is to make topology geometry based conferences every year to honor the memory of Sam, where we can hear some of the leaders in the field talk about the different advances in the state of the art in geometry and topology, both from Mexico and the rest of the world, with an important Mexican component, also to honor the memory of Sam. And every year we are then to have a keynote speaker that kind of ups the ante, that sets the standard very high, so that we have something comparable to the Adam or the Lefschetz, but in a more gregarian social setting. So it's a bit of a different spirit than in the other two events. Needless to say, Sam influenced Mexican mathematics and world mathematics very deeply. Just recently, Avanzado Perspectivas asked me for a 1,000-word contribution called The Influence of Gitler. And there, perhaps the main point that I wanted to make in this thing that's going to be published soon is that while you could learn amazing mathematics talking to some everything, I mean, he was a walking encyclopedia of topology and other things. The most important aspect of Sam's legacy was dual. On the one hand, he was a founding member of both the School of Physics and Mathematics of the National Politécnico Institute, where many of us studied, and at the same time of the CINVESTAV, the whole research institute, one of the original researchers, the youngest one at the time, and one of the two original members of the mathematics department, together with Jose Adam Gitler, two names that are hard to separate, both in mathematics and life and legacy, of course. And that's one of the fundamental aspects. Founding institutions that survive and thrive, it's a highly non-trivial task, especially under the conditions that they did it. But more importantly, in my opinion, there was this flame of passion for mathematics in Sam, up and until my very last conversation with him, the very last conversation with him. Plato, in his 7th letter, compares mentorship more to a flame that is burning, and then the young people come and steal a bit of the flame and they burn themselves, rather than like a data transmission packet. So it's this burning flame, and then the young people come and burn themselves with their own light. And this is what Sam did marvelously. His passion was sincere, deeply authentic, and unstoppable, down to the, I still remember the mathematics of our very last having to do with dark things and conversation. So I want to honor Sam's memory, clearly, with these conferences that hopefully will also maintain the topological geometric spirit of his legacy at this mathematics department that carries on the tradition. That being said, I think for this first conference there could be no one better than only, Ralph met Sam very early on in his career, but and ended up solving a fundamental problem in topology, in which Sam did important advances previously, and using some of the results of Sam. But also, and not only they were friends for many years, but also Sam also carries this, Ralph also carries this tradition of mentoring many students all over the world that have become very productive and good mathematicians. Ralph is also one of the, at the pure accomplishment level, Ralph is one of the leading topologists in the world, and he solved one of the most famous problems in differential topology in the history of the subject, and then has contributed actively to the interaction between symplectic geometry, algebraic topology, algebraic geometry, and mathematical physics with enormous creativity. So, being one of the most original topological minds of the second half of the 20th century and the beginning of the 21st, I introduce Ralph Cohen, that's going to speak about comparing topological field theories.
Well, thank you all. It's a real pleasure to be here. Yes, I met Sam when I was a graduate student, and he looked the same as he does in this picture. It's a marvelous picture. And I remember giving my first talk in a little seminar when I was a student and having Sam sit in the front row, sort of where Ernesto is now. And I was just worried, oh, what if I say something wrong? What will Sam? And he was just terrific. So it's kind of, I almost expect Sam to ask questions during this talk. It's such a nice picture. I've, over my career, enjoyed the opportunity many times of coming to Mexico, various places within Mexico, and I've made very good friends here, and that's been an important part of my career. And I was thinking about this yesterday. Among Sam's many contributions was the fact that he helped the relationship between the topology and geometry communities in the United States and Europe, but I think in particular in the United States, to connect with the topology and geometry community here in Mexico. And it had a great effect in both directions, and I really hope in Sam's legacy that will continue. Anyway, so I would like to talk, as Ernesto said, about comparing topological field theories. One comes from algebraic and differential topology, so-called string topology of a manifold, and one comes from symplectic topology, Floer theory. This is joint work with Sheel Ganatra. Sheel has been a postdoc at Stanford. His background is in symplectic topology. And what we did is that we proved a conjecture from the early 2000s relating these two topological field theories that I mentioned. So we will have a closed-oriented manifold that will be fixed M throughout, and we will describe two topological field theories, and the goal is to prove that indeed they are equivalent, which had been conjectured 12, 13 years ago. So first of all, what is such a field theory? There's been lots of contributions to this over the years, including by Ernesto. The original axioms for field theories were described by Atiyah, Witten, Siegel, with many additions over the years, including more recent ones by Kontsevich and his collaborators, Soibelman and Vlasopoulos, as well as Jacob Lurie. So the kinds of field theories I'm going to be talking about are two-dimensional field theories. So the objects of study are one-dimensional manifolds, and they could have boundary. So what is that? It's just a bunch of circles and intervals. The additional feature, which is encoded in this term open-close, the additional feature is that the boundary endpoints of the intervals will have labels. And so there's a fixed labeling set. From the physical theories, that labeling set usually denotes boundary conditions of some sort. And in fact, they will in these two topological theories as well. They're referred to often as branes, D-branes, in the literature. But abstractly, it's just a set. So you have a set, script D, and you label the boundary endpoints of the interval points in D. And those are the objects of study. And then one also studies cobordisms between these one manifolds. So a cobordism between one manifold is a two manifold, a surface. This is a cobordism of manifolds with boundary, which is a notion that's been around since the 1960s, so there's nothing new here. The only additional feature here is that one wants to keep track of this labeling set. So it's the only extra bit of information. So strictly speaking, an open-closed cobordism is a surface. It's between two objects, C1 and C2. So here's C1, it's a circle and three intervals. Here's C2, three circles and two intervals. And they're labeled. The boundary endpoints are labeled lambda 1, lambda 2, lambda 2, lambda 1, lambda 3, lambda 4, and so forth. So you have a surface. It's kind of an ugly looking surface the way I drew it, but I want to emphasize the fact that it's meant to go between C1 and C2. So what does that mean? It means that the boundary of the surface is partitioned into three parts. The incoming part, which is C1, this circle and these intervals, the outgoing part, which is C2, and everything else, which I've colored in red. So there's some boundary circles in the middle, and there's some intervals. Again, drawn from the physics literature, the remaining part of the boundary is sometimes referred to as the free part. Again, the additional feature here, this labeling set, is encoded by labeling the components of this free part of the boundary, this red part, by elements of that set in such a way that it's compatible with the labelings on the incoming and outgoing ends. So that's the data. Now, it doesn't look like a very nice surface, but it really, it's interesting. So tempted to point this way with the laser pointer or the page turner, but I should point toward the computer. Anyway, the surface is just a smooth surface, and you can think of it as on the boundaries of the smooth surface, there are certain intervals, including perhaps an entire boundary circle, that are identified and labeled. And somewhere in here also it's described which are the incoming and which are the outgoing parts. The black parts of the boundary are the incoming and outgoing parts together. So what does a topological field theory do? We'll call it F. It assigns to an object, namely one of these one manifolds with boundary and labels, some kind of algebraic object, like a vector space or a chain complex. Again, in physical applications, it usually wants some analytic content to that vector space, like a Hilbert space. But it assigns to it some kind of algebraic object of that sort. And it assigns to one of these cobordisms between these objects an operator between these algebraic objects. It could just be a linear map between vector spaces, or it could be a bounded linear transformation between Banach spaces or Hilbert spaces, or a map of chain complexes and so forth. It needs to satisfy certain conditions. The terms that are used is it must be monoidal and respect gluing. So what does that mean? It means that if I take the disjoint union of two of these one manifolds, I should get the tensor product of these algebraic objects. Well, so that tensor product needs to be identified carefully. Category vector spaces, we know what tensor product means. Category of some topological vector spaces. You have to say carefully what you mean by the tensor product. Tensor product of chain complexes is fairly well understood. But notice I didn't write equal here. I wrote something that I usually mean to represent homotopy equivalent. So it's equivalent to that in part of the technical, in fact a good part of the technical issues in this business is getting a handle on what does equivalent mean. Is it homotopy equivalent? If so, do you keep track of homotopies? Do the various choices of homotopies need to be compatible in some way or another? So that's a technical issue. But this is the monoidal feature. And the gluing feature is really described by this picture. If you have two surfaces, one from whose outgoing component is equal to the incoming component of the other, you can glue them together and you form a new surface, and the operator corresponding to the glued surfaces is the composition. And actually I made a mistake here. I did write equal. I don't really mean that. I really mean equivalent to or homotopic to or something within this the appropriate notion of homotopy or compatible homotopies, coherent homotopies. So the examples that we're going to study, the first one is the string topology of a manifold. And I'll call the field theory S sub m. So the manifold will be fixed, closed-oriented manifold. String topology was introduced about 15, 16 years ago by Chass and Sullivan. And it was brought into the world of homotopy theory by a work of myself and John Jones. And various field theory aspects of it were studied by a variety of people and continue to be studied. And the list by no means is exhaustive. So let me just describe some of the properties. The field, I should say, with certain exceptions, the field theory properties that are known about string topology take values not in chain complexes or Hilbert space. They take they take values in just graded vector spaces. It has to do with homology. So sometimes it's called a homological field theory. Anyway, let me tell you what D is. The labeling set is the set of closed-oriented submanifolds of the fixed manifold M. And I didn't say this, but I should probably have written connected submanifolds. So I include a point, and I include the whole manifold. Don't include the empty set. So that's what D is. And they will play the role of certain boundary conditions, as I mentioned earlier. So let me just tell you some properties of this field theory. It assigns to a one manifold in this case, a graded vector space. So what does it assign to a circle? It assigns the homology of the loop space, the free loop space. The map L of M denotes the space of maps of a circle to the manifold, the free loop space. I didn't write this down, but we take coefficients in a field. It could be any field of any characteristic, but a fixed field. What about, this is meant to denote an interval with labels in D, so they're labeled by submanifolds. Then it assigns to that one manifold the homology of the space of paths in the big manifold that start in the submanifold, in one submanifold and end in the other. So boundary conditions. In general, for a general one manifold with labels as I described, it assigns to it the homology of the mapping space from that one manifold to M. And this notation is just meant to mean that it respects boundary values. So on that one manifold, the boundary endpoints are labeled by submanifolds. So the maps have to take those boundary endpoints to the various submanifolds that label it. That's what I mean by this notation. What do you get? What happens when you have a cobordism between one manifold? Then you start by looking at the maps of the surface to the manifold. Again, that respect these boundary conditions. So recall, on the surface, you had those red parts of the boundary, the so-called free part of the boundary, and each component of which was labeled by a submanifold in this case, abstractly labeled by an element of the set D, in this case a submanifold. So you want maps of the surface that take those intervals to the various submanifolds that label those components. And that's what this mapping space right here denotes. And notice you can restrict, from this mapping space, you can restrict to the incoming part of the boundary, and you get the maps from the incoming one manifold to M, or you can restrict to the outgoing part of the boundary. So what do you then do? Well, the value of the field theory on that surface should be in this case, a linear map of graded vector spaces. The vector space corresponding to C1 is the homology of this mapping space. The graded vector space associated to C2 is the homology of that mapping space. So how do you get there? Well, you do some kind of push-forward map. From the homology of the mapping space from C1 to M into the homology of the mapping space from the whole surface to M. This is a backwards map. I like to tell the story of Jack Morava says that it's often written with this exclamation point because you're surprised it even exists. So it's sort of a surprise map, but it's a push-forward map. It's an intersection map, and I'll say a little bit more about that. But then once you have the map to this homology of the mapping space, then you can just restrict to the outgoing part of the boundary. And that's what it assigns to a surface. So pretty clearly, defining this push-forward map is really the technical aspect of this theory and understanding its properties. The way a physicist would define it is using Feynman diagrams. Roughly speaking, the geometric idea is an element in the homology of the mapping space, or element of homology of anything, is a family. An element in HK of X is a k-dimensional family in X. So if you start with a k-dimensional family of maps from C1, you want to intersect that with those maps that come from maps from the entire surface by restricting to the incoming boundary. So there's far fewer of those, so you want to intersect those so that there's a dimension shift, but that's where the intersection theory comes in. And then you get a family of maps from the surface, and then you restrict. It's been defined in many different ways in the literature. Chas and Sullivan's original idea was to use transversal intersections of singular chains. In Jones and my work on a homotopy theoretic perspective, we use Pontryagin-Thom construction, which is how intersection theory is done in algebraic topology usually. There have been cobordism views of intersection theory. There have been descriptions and differential forms and the like. And it's been done in other theories like K-theory, where these push-forward maps could be defined in other ways. So that's sort of the technical aspect, but this is what happens. In this case, when you have cobordism just between circles, no intervals here, then you get operations from the homology of the free loop space tensor itself p times to that tensor itself q times. We have the incoming part is p circles, the outgoing part is q circles. Now, really, I never said that it only depends on the homotopy type or even the topology, the homeomorphism type of the surface. Namely, given a surface, you get these operations. Now, it doesn't depend point-wise on which surface you're talking about, but it does depend in families, and one encodes that in terms of homology. So more generally, if you look at the moduli space of all surfaces, it's the same moduli space used in algebraic geometry or Riemann surface theory or symplectic geometry. You look at the moduli space of all surfaces, then you get operations that are parametrized by the homology of that space. And that's particularly interesting in topology because those moduli spaces are models for the classifying space of the diffeomorphism groups in the surface, an object of really quite fundamental interest in geometry. So that's one of the, I think, the attractive features of this subject. It involves algebraic topological techniques. It involves differential topology, viewing loop spaces and path spaces as infinite dimensional manifolds. Some analytic issues involved in doing that. And it also touches on some algebraic and symplectic geometry because the role of the moduli space of surfaces is fundamental here. Of course, when your cobordism is a pair of pants, you get this product, and that's the original loop product that Chas and Sullivan defined 15 or 16 years ago. So the other example I want to talk about is the Floer field theory of the cotangent bundle. So let me describe it. Floer theory, for Andreas Floer, who did most of his work in the late 80s and early 90s, really was helped to revolutionize symplectic topology geometry. And so it's a symplectic, it's in some ways like an algebraic topology for symplectic topology. And in this case, we're going to study the cotangent bundle of manifold, which from your classical mechanics, one knows has a canonical symplectic structure. It's inherited from the differentiable structure of the manifold. So if you're not familiar with that, let me just give a quick reminder of how that goes. So consider the cotangent bundle as a vector bundle. So there's a projection map. And where does the symplectic structure come from? Well, let's take a point in the cotangent bundle. So a point in T star of M is given by a point in M and a cotangent vector at that point. So in other words, a linear map and from the tangent space at X to R, a dual element of the tangent space. Then start at the tangent space at that point of T star of M. So if M is an n manifold, T star of M is a 2n manifold, 2n dimensional manifold. It's not compact anymore, but it's a smooth manifold. And so you can look at its tangent space, and then you can differentiate the original projection map, and you end up in the tangent space at M. And then follow it by this cotangent vector to R. So it's a little procedure. It takes any point in T star of M and gives you a dual element of the tangent space of T star of M. In other words, it's a one form in T star of M. And it's referred to as the Liouville one form. And its exterior derivative is a symplectic form. It's a non-singular skew-symmetric form. And so that only depended on the smooth structure of the manifold, because it obviously depends on T star of M. And an important question that in symplectic topology, and it's been there for many years, is how much of the differential topology of the manifold does the symplectic topology of T star of M represent or encode? One other bit of symplectic theory associated to this, in string topology, you saw that we were studying submanifolds in the manifold as well. When you have a submanifold, then you can look at its conormal bundle, which is a subbundle of T star of M. This is a vector bundle over N, the submanifold. The fiber at a point X are just those cotangent vectors that vanish identically on the tangent space of N of the submanifold. So it's a conormal bundle. If you do the algebra, the very quick little napkin exercise, you'll find that conormal bundle as a manifold itself is always n-dimensional. In other words, half the dimension of T star of M. It doesn't matter whatever n is. It's always n-dimensional. In fact, for example, when n equals m, then the conormal bundle is trivial zero-dimensional bundle, so the conormal bundle is M itself. It's the zero section. When n is another extreme example is when n is a point. The co-normal bundle is, well, all you have is one fiber, the cotangent fiber at that point, and it's all in the co-normal bundle. So the co-normal bundle for a point is a cotangent fiber, which is the vector space, again, n-dimensional. One is sort of, the first one is kind of horizontal, the second one is vertical. So these, it's not a hard exercise in basic symplectic theory to prove that such a thing is always Lagrangian, which means that the symplectic form vanishes identically on the tangent space of the submanifold. Now, given an exact symplectic manifold, in other words, a manifold whose symplectic form, the 2 form, is exact, like the situation we have in the cotangent bundle, then you can define the symplectic Floer homologies, one of the earliest things that Floer did about 30 years ago, maybe more than 30 years ago. And I'll call it SH star then, symplectic homology. It's defined using a kind of infinite dimensional Morse theory, defined on the free loop space of n, of the symplectic manifold. So for Morse theory, you need a function, a Morse function, with non-degenerate critical points, and then you build a chain complex out of that and you compute its homology. So let me just say a few words how that's done here. What is the function? As I said, it's called the symplectic action. I'll call it script A. And what do? If you have a loop in n, so it's a map from the circle to n, you can pull back the one form. So omega is d of the one form. You can pull back the one form by that loop, and you now have a one form over the circle. You can integrate it over the circle, you get a number. That's a function. It's sometimes called the symplectic area, because if we assume we're in the component of the loop space where the loops are contractible, which would always happen, for example, if the manifold is simply connected. If the loops are contractible, that means any loop can be extended to a map of a disk. And if you take an extension of that map of the disk, you could pull back the symplectic form over the disk and integrate it over the disk. Why is that called area? Well, again, the symplectic form is a skew-symmetric non-degenerate form. If we really want to compute the Riemannian area, you would have a symmetric non-degenerate form, namely the metric. You pull that back and integrate it, and that's the area of the disk. So here you're pulling back the skew-symmetric form, so it's sometimes referred to as the symplectic area. And a little exercise with Stokes' theorem is that it doesn't depend on which way you extend to the disk if you're in a given component. Okay. If it's not exact, you can fiddle around and define this theory as well. It's usually easiest to work in the universal cover or some covering space of the loop state. But we're working primarily with the cotangent bundle, so it'll be exact, so I'll stick to that case. So you have this function. It's not non-degenerate. The critical points may be degenerate, so you have to perturb it, just like you do in Morse theory. Here you want to perturb it to keep the sort of spirit of the symplectic structure, so you perturb it in a particular way using a Hamiltonian function, a time-dependent Hamiltonian function. I'll just sort of brush that under the rug for a moment, but you perturb it until you get non-degenerate critical points. You also have to choose an almost complex structure. So if you, again, this is sort of a linear algebra exercise. If you have a symplectic structure, then you have an almost complex structure. The symplectic group of R2n is a homotopy equivalent to the unitary group, UN. So you can find an almost complex structure, and the number of choices is contractible. But you pick one, and that almost complex structure, together with the symplectic form, actually defines for you a Riemannian metric. And so remember from Morse theory, in order to define the Morse chain complex, you need a Riemannian metric so you can talk about gradient trajectories, gradient flow lines. So you need that here too, and the way you get it is by choosing, after perturbation, choosing an almost complex structure. And then you get a chain complex that's generated by the critical points of that perturbed symplectic action, and the boundary maps are computed, like in Moore's theory, by counting trajectories between the critical points. Now here, this is defined on the loop space. So a trajectory of loops, a curve of loops, is a map from a cylinder. So you have a map from the cylinder to M that satisfies the gradient flow equation, differential equation. And one observation that Floer made in this paper, and in other contexts Gromov made, is that that equation is the Cauchy-Riemann equation coming from this almost complex structure. It's been perturbed. It depends on J, and it's sort of a perturbed Cauchy-Riemann equation, and so is often referred to as a pseudo-holomorphic cylinder. Satisfies that perturbed Cauchy-Riemann equation with respect to J. It depends on J. So that's how this chain complex is defined, and the resulting homology is the symplectic homology. And then there are theorems to the extent that it doesn't depend on choices. One of the choices we made was this Hamiltonian. It only depends on sort of asymptotic conditions of the Hamiltonian. So, but there are precise theorems about to what extent it's invariant of these various choices. So that's the symplectic homology. Now let's go back to our case of interest, the T star of M, the cotangent bundle. In that case, the symplectic homology has to only depend on M, because the symplectic topology of T star of M only depends on the smooth structure of M. And indeed, it only depends on the homotopy type of M, because a theorem of Viterbo from the late 90s is that the symplectic homology of T star of M is the homology of the free loop space. More recent and frankly more complete proofs have been done by Almudando and Schwartz, Solomon and Weber, and others, Abu Zaid, Thomas Krah, others as well. So this is the first bit of contact with this other theory, string topology. This is true as I've written it if M is spin. I assume that the manifold is oriented, so that means the first Stiefel-Whitney class is 0. If it's spin, that's just equivalent to being the second Stiefel-Whitney class being 0 as well. If it's not 0, this is true with some twisted coefficients. That was only observed recently in the last 5-6 years. Namely, it was thought of for probably 15 years that this was true without any twisting. But you have to be more careful. The orientations can be very confusing in this business. So let me tell you a little bit some properties of the Floer symplectic field theory. I'll call it simp T star of M. In this theory, again, let me tell you what some of its values are. Its values will be in graded vector spaces, just like before. Its value on the circle would be the symplectic homology of T star of M. And you can imagine more generally, symplectic homology of whatever manifold you have. I should say this field theory has not been worked out in full detail in large generality, but it has for certain kinds of exact symplectic manifolds, including the cotangent bundle. So again, the value on the circle is the same as the value of string topology on the circle. So again, that's the first bit of contact. What about on an interval with labels in submanifolds? Then the value there is a somewhat different kind of Floer theory, related but different, and it's called the Lagrangian intersection Floer homology. Again, due to Floer. Soon, I'm not sure of the exact history, but soon after his paper on Floer, the symplectic homology. So this kind of theory is when you have a symplectic manifold and two Lagrangian submanifolds, as you do with its these conormal bundles. So how do you define this? It's again defined by a chain complex that's generated by points. In this case, it's the intersection points of the two Lagrangian submanifolds. You may have to perturb to make the intersections transverse. And say P and Q are are two intersection points between N1 and N2, then the way you compute boundary homomorphisms is not by counting holomorphic cylinders with boundary values, but you count holomorphic disks, J holomorphic, pseudo-holomorphic disks, maps from the disk to T star of M that satisfy the same Cauchy-Riemann equation, perturbed Cauchy-Riemann equation. But now the boundary conditions are, on one semicircle it has to go to the conormal bundle of N1, the other to the conormal bundle of N2, in general the two Lagrangians you're working with, in such a way that at the intersection points it goes to the intersection points you're kind of counting. And you get a chain complex. Its homology is the Lagrange intersection homology, and it's been worked out that this does have field theoretic properties. The value on a pair of Pants cobordism is a product in symplectic homology that is known as, of all things, the pair of Pants product. And that's computed by counting J holomorphic curves from the pair of Pants to T star of M. So from this perspective, let me state the theorem with Shield-Ganatra. Namely, there are two-dimensional, open-closed, here's a term I haven't defined yet, but I will in a minute, positive boundary topological field theories, SM and simp T star of M, that take values in chain complexes, not in graded vector spaces, so the theories are refined. They take values in chain complexes. That have the property that when you pass to homology, they're the theories that we've just discussed, the symplectic, the string topology or the symplectic Floer theory. And furthermore, as theories, there's a natural equivalence between them. So they're equivalent theories at the chain complex level. So not only do these theories agree on a circle, not only do they agree on a pair of Pants cobordism, give you the same ring structure, but the entire theories agree at the chain complex level. One of the features of doing it at the chain complex level is that there are certain vanishing theorems known when certain of these operations are zero. But the vanishing theorems, it's not so important that you get zero, but it's why you get zero. So on the chain complex level, you get zero because of very specific reasons, chain null homotopies. Well, these null homotopies give you higher order operations, and this would say those higher order operations also agree. And these higher order operations geometrically are often used to get operations corresponding to the boundary, the homology at the boundary of moduli space when you start compactifying. So there's geometric reason to get at the chain complex level. So what are the techniques? Well, there have been fairly recent classification methods of topological field theories. Oh, by the way, before I get to this, I should tell you what I mean by positive boundary, because I didn't here. So as I said before, a field theory will assign to a cobordism, a surface, a linear operator. Positive boundary means it's a requirement. It sounds good, positive boundary sounds positive. But really it's it's sort of a detriment to the theory. It says that there's a requirement, namely that the surfaces that you can work with have to have non-empty boundary. It doesn't give you operators or really numbers, invariants corresponding to closed manifolds, for example. It has to have boundary. And there's usually an orientation like a left positive boundary or a right positive boundary, or incoming versus outgoing. And that has to do with the requirement that maybe on the incoming side you require boundary of the cobordism, but maybe not on the outgoing side, or vice versa. And that's related to these, like the algebra involved from the Chas-Sullivan product, having a unit, where there's a co-algebra that may have or may not have a co-unit. Questions of that sort. Anyway, so as I said before, there have been a fair number of recent works in the last 10 years or so of classifying these things. Probably the most comprehensive is the cobordism hypotheses of Lurie, but it's the least detailed. The details of the cobordism hypothesis, I think, are fairly accepted in dimensions 2, but this is meant to give a cobordism, to give a classification of field theories in all dimensions, and a lot of the foundations have not yet been established. He has about 6 or 7 years ago, he posted on the archive a sketch of the proof and statement of the cobordism hypothesis, and the sketch was 100 pages long. So it's a very in-depth, sort of revolutionary approach. Still not clear how revolutionary. Will it completely revolutionize the field? Some people believe so. Or is it just a mountain of machinery that is used when you need it? But it's clearly a useful bit of machinery. There's an older version due to Costello, which is strictly in 2 dimensions, that sort of motivated us, although his axioms were rather rigid, too rigid for these purposes. Kontsevich and co-authors, I don't know why I forgot to put Soibelman and Vlasopoulos, have a theory that's chain complex valued. It has the right level of flexibility, and frankly, it doesn't involve nearly the amount of machinery here. So we focused on this approach, although we'll say a few words about how the different approaches are related. But roughly speaking, in all of these approaches, in the language used, I think it was coined by Costello about 10 years ago, that a 2-dimensional, one of these positive boundary open-closed field theories are classified by Calabi-Yau algebras or categories. And there's this other term that I didn't say, A-infinity, or in Lurie's language, infinity categories. That language has to do with what I was saying earlier about the choices of equivalences, of homotopies, and the coherence between them. So why is it called Calabi-Yau? Many of you are familiar with Calabi-Yau manifolds, which are of fundamental importance in differential geometry and in string theory. And I'll try to say a word or two about where that comes from, where the terminology comes from. But what we show using these kind of results is that there's a string topology category that I defined in a work with Blumberg and Telemann several years ago. That category is generated by submanifolds, and the morphism spaces are these paths between the submanifolds. That has a Calabi-Yau structure in this sense. The Fukaya category, which you have for any symplectic manifold, has a Calabi-Yau structure in this sense. This was proved by Schiele in his thesis. And that what we prove is that these 2 categories are equivalent in such a way that they preserve this Calabi-Yau structure. By the classification theorems, the field theories corresponding to them are therefore equivalent. And then we have to prove that those field theories are indeed realized string topology and Floer field theory. So that's the rough outline. So why is it called Calabi-Yau algebra or category? First of all, these categories, for these purposes are all enriched over chain complexes. This Calabi-Yau notion that Costello identified is sort of the algebraic property that's possessed by the category of coherent sheaves of a Calabi-Yau variety. That's the underlying category. As you'll see in a moment, it's a duality property. It's very similar to Frobenius that Ernesto and others have studied. But Frobenius up to a certain kind of homotopy and a certain equivariance involved in it as well. So, you could go backwards. You look at a Calabi-Yau variety, you look at the category of coherent sheaves. By these classification theorems, there's a field theory, and indeed this is the B-model theory and string theory. So this is what motivates it. It sort of abstracts or categorifies, if you will, the properties of the category of coherent sheaves of a Calabi-Yau manifold. For purposes of the discussion in the last 10 minutes, I'm going to talk in the language of algebras. If you have a category of chain complexes, well, imagine, let's do a simple example. Imagine a category with only one object. So the objects aren't very interesting, there's only one thing. But what's interesting are the morphisms from that object to itself. By definition, it's a chain complex. But you can compose, you have to be able to compose morphisms. So that means you have a product on that chain complex. It's nothing more than a differential graded algebra. So I'm going to use the language of differential graded algebras to describe these notions. We think of, or I think of, a category in this setting as like an algebra with lots of objects. But let's work in the category of algebras because we're more familiar with this language, taking tensor products of modules and stuff like that, where in categories it's less conceptual, harder to understand, but it can be done. So let's do some algebra. Algebra geometry is fun, it's inspiring, but algebra is good for the soul. So let's do some algebra for a few minutes. And I think Sam would agree with that. So suppose you have an algebra, an A infinity in the sense of Kontsevich, or infinity algebra in the sense of Lurie. And we can consider its Hochschild chains. Now typically when you learn about Hochschild homology, you're given a specific chain complex. Hochschild homology is the homology of that chain complex. But abstractly what it is the algebra is a bimodule over itself. Right? You can multiply on the left, you can multiply on the right. Another way of saying that is the algebra is a module, say a left module or a right module, over A tensor A op, the opposite algebra, left and right multiplication. And Hochschild chains is just the derived tensor product of those things. So if you're not familiar with this derived language, all I mean is take one of these, say that algebra A, and take a free or projective resolution of A as a module over this A tensor A op, and then take the tensor product with A over it. That's the derived tensor product. Hochschild homology is the homology of the resulting chain complex. Now, I think it was Alain Kahn who noticed back in the early 80s that this chain complex carries with it a circle action. Strictly speaking, what I mean by that is you look at the singular chains of a circle, which is equivalent to an exterior algebra in one generator, the sort of fundamental class of the circle. And that has an operator on the Hochschild chains. It's often referred to now as the Kahn B operator. But it's one way of saying it's a module over this. And the cyclic chains can be viewed as the orbit space, again, homotopy orbit space of that action. So you take the derived tensor product with this trivial module over that. And that's its homology is the cyclic homology. Kahn originally worked over field of characteristic 0, so the algebra is a little easier, but Laudet and Quillen and Segan and Fagan described it this way. So let me tell you what I mean by Calabi-Yau. There's actually two notions of Calabi-Yau that are due to Kontsevich and his collaborators. Again, it's very similar to notions defined by Costello and Luria. But I'm going to talk about a compact Calabi-Yau. So suppose the algebra is compact, and that just means it's perfect as a K module, and perfect just means its homology is finite. It's a finite dimensional vector space over the ground field. Like the singular chains of a manifold. Singular chains of anything is infinite by any measure, but its homology is finite. That's where the compactness comes in. Then a compact Calabi-Yau structure, CCY, is a map, sometimes called a trace map, from the cyclic chains to the ground field. Simple as that. And it satisfies a certain property. And the property it satisfies is, well, again, the cyclic chains is the orbits of the Hochschild chain. So there's like a projection map from the Hochschild chains to the cyclic chains, then you follow it by this map. The Hochschild chains is a tensor product. So ultimately you get a tensor product. You get a pairing from A tensor A to K. And the condition is that that pairing is homotopy non-degenerate, meaning that the resulting adjoint map from A to its dual is an equivalence. And it's an equivalence since it factors through this tensor product over A tensor A out. It's an equivalence as bimodules, and that's kind of important. So this is an old notion of Frobenius up to homotopy, except you have this extra circle action coming in, and you have this bimodule structure that you're preserving to. There's a related notion called smooth Calabi-Yau. It involves negative cyclic chains. The negative cyclic chains are like the fixed points of the circle action. So you take homomorphisms from a trivial module to it, maps from some, like a point to a space with a group action, have to land in fixed points. So this is the notion of homotopy fixed points. Its homology is the negative cyclic homology that I think was first introduced by Goodwillie. An algebra is said to be smooth as opposed to compact if it's perfect not over the ground field but as an A bimodule. In other words, it's perfect as a left module over A tensor A out. So again, it's equivalent to a finitely generated module over A tensor A out. So it's a finiteness condition. Let A shriek be the bimodule dual. What does that mean? Well, if you have a module over a ring, how do you think of the dual? You look at homomorphisms from that module to the base ring. So that's what I'm doing here. For those of you familiar, this is a kind of Hochschild cohomology. But just take this homomorphism. And the smooth Calabi-Yau structure is not a map from the cyclic chains to a ground field, but it's a map from the ground fields to the negative cyclic chains. It's a dual thing. Sometimes it's called a cotrace. Well, a map from a ground field is just an element. So it's given by an element of these negative cyclic chains, a little bit of homological algebra, and I describe a little bit here, says that you can take a cap product with the class that you get in Hochschild chains, and you'll get a map from the bimodule dual to itself. And the requirement is that that be an equivalence. So it's self-duality. Oh, what's that? It's self-duality, but not over the ground field, but rather over as a bimodule. So again, it's a different kind of, sort of a dual kind of self-duality. So that's smooth Calabi-Yau. Kontsevich conjectured and Ginzburg proved that if an algebra is both smooth and compact, then these two notions are equivalent to each other. But as you'll see, examples, that doesn't always happen. In fact, in the examples coming from topology, it almost never happens. But the theorem, roughly stated, is that if you have a category or an algebra with either one of these structures, it gives rise to a field theory in a canonical way. And that the value of the field theory on the circle is the Hawkshill chains. The value of the field theory on an interval is the chain complex of morphisms. The value of the field theory on this disk, which is viewed as a cobordism from 3 intervals to 1 intervals, is given by the composition laws in the algebra category. But it gives rise to an entire field theory. And again, what we prove is that the string topology category that I mentioned and this Fukaya category both have smooth Calabi-Yau structures, and the associated chain complex value theories yield string topology and Floer field theory, and that these theories are equivalent as Calabi-Yau categories, smooth Calabi-Yau category. And I don't know when I started or when I should quit. I always, when I'm in the audience, I always think, when I hear the speaker say, "What time did I start?" I always think, "Oh, that's a bad sign." So now I've done it myself. So I'll only take at most 5 more minutes. I described this category a little bit. And in order to make a rigorous category out of string topology, ultimately what's used is a very twisted form of Poincare duality. So ultimately it doesn't have much to do with it being a manifold other than the chain complexes satisfy Poincare duality. But one thing to observe is that the endomorphisms of a point is a submanifold, in this category is the chains of the loop space. And I should say, the basic thing we proved is that this string topology category can be viewed as a subcategory of the category of modules, perfect modules over the loop space. So it's all has to do with understanding modules over the loop space, which goes back 40 years to the work of Waldhausen, that if you really want to understand differential topology, you have to understand the loop space. So that's interesting. So the endomorphism points that change the loop space, so this clearly generates the entire category. Now, several years ago, Abuzai proved that the endomorphisms in the Rapp-Fukaya category of the cotangent fiber is also equivalent to the chains of the loop space. And that this cotangent fiber, viewed as a Lagrangian submanifold, generates this Fukaya category. So that's the beginning of what we are working with. Why is there this Calabi-Yau structure? There's a little bit of homological algebra, Morita theory, basically saying that if you have a subcategory of a big category that generates it, then one is smooth Calabi-Yau if and only if the other is. So in our case, all we have to do is show that the chains of the loop space is smooth Calabi-Yau as an algebra. That was the first observation. And in my notes here, I didn't realize how long this talk would take. In my notes here, I go through an outline of a proof of this, but suffice it to say, that fact, that knowing that the chains of the base loop space is smooth Calabi-Yau is ultimately that algebraic property of the chains of the loop space that's inherited from the fact that the manifold satisfies Poincare duality. Knowing that, and working for a couple days, you can prove this. It's not that hard, and it's again Poincare duality in various twisted forms. And the Calabi-Yau structure, remember, is given by a class that's ultimately represented by the fundamental class of a manifold. So again, these are these homological algebra calculations using Poincare duality. Now I mentioned Ganatra proved that the Fukaya category is smooth Calabi-Yau in his thesis. Moreover, I mentioned that Abudandolo and Schwartz gave a proof of Viterbo's theorem, saying that the symplectic homology of the cotangent bundle is equivalent to the homology of the free loop space. What we did is really take apart their proof and modified it a little bit to see that it can be used to define a functor between categories. The Fukaya category on the one hand and the string topology category on another hand relates the Floer theory to the symplectic topology. And we show it's an equivalence of categories using not the result of, but the arguments of Abu Zaid. So it uses results of several people. Now we need to know that these Calabi-Yau structures are preserved, and it turns out to be technically the hardest part from both the algebraic topology side and the symplectic topology side. There's just one other feature I want to point out, and that is, what is this left and right positive boundary? How does that correspond to smooth and compact Calabi-Yau? Well, the theorem is it corresponds on the algebraic level, for those of you familiar with this algebra, to the notion of Cazul duality. It turns out that if A and B are Cazul dual, namely the endomorphisms, the ground field over A, which is an algebra, homomorphism, just compose them. If that's equivalent to B, and if A is equivalent to the endomorphisms, the ground field over B, then if A is smooth Calabi-Yau, if and only if B is compact Calabi-Yau. So Cazul duality relates them. And moreover, the field theories that are associated to these algebraic properties as Cazul duality are dual to each other, just algebraically dual. It was known that their Hochschild homologies of Cazul dual algebras are linearly dual. But what we're saying is that not only the values of the field theory and the circle, where it's this Hochschild theory, dual, but all the homomorphisms, all the linear operators are dual operators. So you get really the same theory. Witten happened to be visiting Stanford when I was working on this, and I talked to him, and he compared this to, in some way, like a baby version of homological mirror symmetry. Because here you have, typically you have mirror symplectic manifolds that give equivalent field theories. Here you have mirror algebras or categories, namely Cazul duality. So that gives you the mirror. They give you equivalent field theories or dual field theories, but the field theories are equivalent. So, and I should just end by saying that we have a conjecture that the Kontsevich notion is equivalent in this world of chain complexes to the Lurie notion. And if that's true, and we're working on this with in joint work with Andrew Blumberg, and if that turns out to be correct, the field theoretic applications of it are even stronger. So I will end there. Thank you very much.
Any questions?
For this finiteness conditions, can you see it somehow from the torus, that it should be some kind of dimension in some sense?
Yeah, you can say it that way. A little bit hard to, if you don't mind, let's talk about it. But it is a consequence of, in fact, the Lurie notion here, it talks about the property of this dimension, and it has to have finiteness properties for the trace map to exist. So ultimately, the answer to your question is yes. But exactly how you see that is a little bit of an exercise, but yeah.
Any other questions?
Is there any interpretation of the trace map, like in terms of duality things related to Montreal-Eaton construction or something?
So, I mean, the canonical example, I should have said this or emphasized this more, is the cochains of a manifold, closure-oriented manifold, is one of these Calabi-Yau algebras. And the trace map you get ultimately gives you a pairing, and it's just the intersection pairing or the cut-product pairing. The chains of the base loop space of a manifold, I did say, is smooth Calabi-Yau. Now, it's been known for years, in fact, maybe the first example that the cochains of a manifold, at least when the manifold is simply connected, and the chains of the base loop space are Cazul dual. So one theory, one field theory has this right-handed positive boundary condition, the other field theory has the left-handed. When you go between them, the co-trace becomes the trace. That's sort of under this duality. But yeah, ultimately it's from intersection theory. By the way, just to throw words around, in the case when your manifold is a k-pi1, like most 3 manifolds, the loop space of the manifold is just 2 equivalents pi, and so the chains of the loop space is the group ring of pi. So we're saying it satisfies this Calabi-Yau condition. What condition is that? It's what is often called Gorenstein condition, a Gorenstein duality. So in some ways this Calabi-Yau condition generalizes Gorenstein, it generalizes Poincare duality. And again, like I said, Lurie, Costello, Kontsevich all have similar but different views. So in some ways the dust hasn't settled as to what's the cleanest or clearest viewpoint.
Any other questions? I have a question. In this work of Matt and Galash's, especially Galash's and Randall Williams,
Yeah.
they have this version where they have this additional structure of a map to,
Yeah.
for example, a VG or whatever.
Mm-hmm.
Can you incorporate that situation here?
Oh yeah, yeah. So that structure is a structure on the tangent bundles of the circles, in this case the surfaces making up the cobordism category. So the structure that I've been using is an orientation, but you could do something similar for any structure, including a map to a target space. So yes. I should say also, field theory can be viewed as a functor from this cobordism category to category chain complexes or something. And you can ask, does it only depend on the geometric realization of the cobordism category? And that's been now understood by sort of physicists and mathematicians. Dan Fried and Greg Moore and others developed the notion of an invertible field theory, and that's exactly one where the Madsen, Weiss, Tillman, Galatius results will tell you exactly, compute exactly what the homotopy type of all possible field theories are.
Well, any other questions? Well, let's thank Ralph again. Thank you very much.